Welcome back to our video module on quantum mechanics. For a while we've been exploring three-dimensional models of, for a while we did the infinite spherical well, and now we've branched out and looked at hydrogen-like models and the types of central potentials that characterize those models. And during this exploration of 3D models, we've seen lots of representations. Today I've put up some representations corresponding to the 2-1, or in particular to the 2-1-0 wave function. So n is 2, L is 1, m is 0. And we've seen things like this, which characterize the magnitude of the wave function. Or we've seen from a radial perspective how the magnitude of the wave function changes as a function of radius. For the L equals 1, when we looked at our spherical harmonics, we started looking at three-dimensional models, as well as 2D plots that orient us along the xy plane and the z-axis. And in addition, we've looked at different ways, from Legendre polynomials to Laguerre polynomials, of representing what's happening both spherically and radially. And if that weren't difficult enough, we also have plots like this that take into account actual phase of the wave function. And to top it all off, our wave function equation, which we may be able to derive, or we should be able to derive at this form, includes both a radial component, which is 2, in this case n is 2, L is 1, we have this right here, as well as a spherical component of theta and phi, which has different dependencies. How can we combine these models to inform our understanding of wave functions in 3 dimensions? Today, we'll be pulling together the various three-dimensional models that we've learned over this unit in Griffiths to construct an actually realistic way to think about wave behavior in simple hydrogen-like models. So to start off our conversation, today we'll be looking at the 2-1-0 wave function, where our n is 2, our L is 1, and our m is 0. And much of that information I've included here in the charts and equations above. This consists of two aspects. For convenience, I've simplified A to represent all of our normalization constants. It consists of a radial component, which tells how things change as a function of radius, and a spherical component, which tells how things change as theta and phi. And this is conforming with our original technique of separating. Right here we show it explicitly, of separating our variables. First, let's look at the spherical component of this equation. Now, if you're like me, this should instantly conjure up images of the spherical harmonics. And if you recall, what we did is we found the spherical equation, then we created two-dimensional plots that can be thought of along the xy axis, the xy plane, and the z-axis. And an instructive tool that we use was to create then a rotated 3D model to represent it. In this, we see that as you go down, L increases. And we also see an increase in nodes. Now we know enough that increases in nodes usually corresponds with an increase in the energy. And we've only been looking at this from a geometric perspective when we first looked at it, but we'll see that in fact, as more energy goes into the spherical harmonics, the nodes increase. So you can imagine, here at the top, there's no nodes, so little energy. And then as more and more energy is applied to these spherical harmonics, you get down to here and you have 3 nodes. The second informative aspect of these three-dimensional models is what happens as m increases. We can see as m increases, the probabilistic cloud gets pushed further away from the origin. Now, to understand this twofold aspect of the spherical harmonics, let's return to the spherical harmonic equation of YLM. Recall that it's really constructed of 3 basic components. The first component is something of a normalization. The second component relies only on m. And the third component is our PLM, which is really what we use to derive these 2D models. What I found to be the best way to think about it is your L component. This is the big driver of nodes. Your L component indicates the total amount of energy going into spherical curvature. So more curvature is more nodes is more energy. The M, on the other hand, is an indicator of how much of that energy goes into increasing curvature about the z-axis. The best way to look at that is look at what M directly influences, your EI to the M phi. Quantized increases in M increase our nodes about the z-axis, which is an increase in energy about the z-axis. And in fact, what you can see if you were to kind of take a look at this three-dimensional model from above, kind of like from up here, you can see that if you're looking, let's say on this one, you'd end up with something that looks like this. From that perspective, you can see more of the wave function's magnitude is getting pushed away from the origin. Conversely, looking at our 2-1-0 shape right here, say along the XY axis, so you're really kind of going horizontally looking at this harmonic, ends up finding something that looks like this up here. And the plus and the minus are indications of phase. Similar in the spherical harmonic 3D model, the red and the green are indications of phase. And so while we're looking related to M, while we're looking at 2-1-0, where 0 is M, we expect a low rotation about the z-axis because our quantized M is at 0. But let's pretend now that we decided to go with 2-1-1, in which case we're increasing here. We're going to increase a node about phi, which means in the z-axis we're going to have an additional node, and that'll be what's going on right here, where if we were to look from above, we'd have something that looks like this. Now, navigating the radial aspect of the overall wave function is a little bit more straightforward. What I've listed out up here with n is 2, L is 1, M is 0, is we see the radial dependence of the wave function, and really what we're looking at here is the magnitude of the wave function as a function of r. And it's important to notice here that we're looking at 2-1-0. So in other words, the L is 1, which means some of the energy has gone towards increasing curvature in the spherical harmonics. So we don't see any nodes here radially. We do see a node here as a function of theta and phi. And down here, I have a graph of the magnitude of the wave function as a function of density, or you could look at it as the probabilistic density magnitude. And you can see that there's no nodes. Rather, the energy has gone to creating a node in the theta and phi direction, or in this case, really in the theta direction. Now, what would happen if instead of doing 2-1-0, instead we did phi of 2-0-0? In this case, our spherical harmonic, we're going to have a 0-0, which is this top one here, no nodes. So in other words, none of the energy is going towards increasing curvature in the theta and phi direction, which means it has to go into increasing curvature in the radial direction. And in fact, what we see here is the radial dependence of the probability density, or the wave function magnitude. And you can see that there's an additional node, that there's increased curvature. It's getting more wiggly just in the radial direction. So even though in the spherical direction there's no nodes, in the radial direction there is. And now we can start to see that as we add energy to our quantum states, basically going from n is 1 to 2 to 3, the overall number of nodes increases, and we can see how that makes sense given our previous illustrations. So one might ask, just for comparison's sake, how might we graph the 2-0-0 wave function here as a function of r? Well, we'd expect that most of it would want to be around the origin, and then there would be a node right here, as more of the energy is going to increasing curvature in the radial direction. And in fact, if I were to pull an image of the 2-0-0 wave function distribution diagram, where we're just looking at a slice through the origin, this is what we get. We have this increased density in the middle. We have pretty much nothing that corresponds to this node, and then a nice wider probabilistic distribution out here. There's a number of great images online. I've included some of the websites and locations in the description of this video where you can take a look at overall wave functions for all sorts of different quantum numbers. I'd encourage you to look at it and really think about what's going on here radially, what is going on here spherically, how is the energy increasing, and how does that inform our understanding of wave behavior in hydrogen-like models? One note I should put in here is that at this point we're saying that LM states are degenerate in N. We'll learn more about superfine and hyperfine structures as we progress through the quantum mechanics. I hope this video has given you something to mull over and chew on, and as well has brought together many of the ideas and the models that we've been looking over the past couple weeks in 3 dimensions.